Stanford, and he'll talk about MDPs with fixed discount factors.
Okay. Thanks to the organizers asking me to give a talk over there. It's my first time to Siemens. So I'm going to talk about Markov decision process with fixed discount. Here I'm not talking about something new or something. It's pretty old stuff, and so it's the policy iteration method, and together with the Simplex method. Okay. So I'm associated with Department of Management Science and also computational CME. Okay. So here's my outline. So I'm talking about the linear programming. So that's the big pictures, and which is underlying and Markov decision process. Then I'm going to give a very quick introduction. What's the Markov decision process, and also what's the Markov process game. Then I summarize a couple of advances in Simplex and the policy iteration method in the past maybe 5 years. Then I'm going to give some remarks and open problems. Okay. So first, linear programming. That's the big pictures. And the linear programming, to me, is remain one of the core computational problems in the current century, in the past century as well. And developed by a couple of giants, and Koopman, Kantorovich, and the middle is George Dantzis. That's the Simplex method. Okay. So amazingly, and linear programming still very, very widely used today, and many people use them to solve practical problems, and also even use linear programming to prove theorems, whatever, some kind of underlying, use some lower bounds duality theories. Okay, linear algebra has very simple algebraic form. Okay, so you basically have X is called decision variables. You give matrix A, which is m by n, okay, which is given. That's counted as a data. You're also given right-hand side B. That's also part of the data. And then you want to decide X, and X has to be non-negative. So you want to minimize this objective function, which is given and objective factors. Okay. Again, this is a standard LP form. X is an n-dimensional vector, needs to be optimally decided. So in some sense, LP is a typical data-driven computational decision model. And you're given ABC, then you output X. So that's the, in the today, A getting bigger and bigger, and M is also getting bigger. So people still constantly search is the better algorithm to solve linear programming algorithms. Okay. From geometry point of view, and linear programming actually is a polygon, and this is counted as a feasible region. You want finding an optimal vertex, which is to have the highest or most favorable objective values. So the question is, how should I search along these polygons and to reach that premium, which is our target. Okay. So two algorithms, which is even up to date, and although many efforts has been made, to me, all the commercial or public domain software is implement either the Simplex method, which is George Dantzis invented almost 70 years ago, by moving from vertex to vertex. Okay, and then somehow, and he can prove, and you can reach the optimal vertex in so-called finite time, number of steps. Another method, which is studied in last century 80s, which is the interior point method, which goes through the interior feasible region and reach the optimal vertex. So although we have a lot of first order or some other method come out, and so far as I know, and this is the two working horses and in this field. Okay. Those new things has not been matured enough to be implemented by any commercial software. Okay, so these two methods, but it's really two different stories. The simplex method, all the theoretical results are somehow very negative. Whenever you develop a simplex method, then people construct the counterexamples. In the worst case, that pivoting rule or simplex method has to be exponentially in number of steps. Okay? But on the other hand, the interior point method is all good news. Even today, we still have people in MIT got a volumetric center, even try to improve it. Okay? But some of those probably is not really implementable, but still traditional classical interior point method has to be implemented. So there was a kind of a disconnect between, and especially for simplex method, and disconnect from theory and practical performance. So today I'm just trying to be positive and bring a couple of good news for simplex method. Okay, so this comes out to solve Markov decision process and game. Okay, I don't know, probably many people here probably all heard about the Markov decision process. So I'm going to give a very quick review. Okay, even with some toy examples. So MDP provides a mathematical framework modeling sequential decision-making situation. The outcome are partly random, partly under control decision maker. That's the theme of this workshop, and uncertainty. Useful study dynamic programming. Actually, many problems can be, especially in the name of dynamic programming, and so can be formulated. And that goes very old days. Okay. There was many modern applications, especially in the learning. We heard about a lot of talk today, somehow which fit into this kind of framework. Okay. At each time step, the process is in count state I. So in this talk, I'm going to say there was M states. Okay. And the decision maker choose action in some set. Okay. That is the AI, A sub A, means the action available for state I. So you can think a state is the agent. Okay, you can play any action or play, you can, okay? Choose the emitter corresponding cost Fj. Then the process responds next time by randomly moving into a new state. Okay, I call it I prime. Then the process and choose action. So this probability, which is not for sure, but which state is going to be end the next time is dependent on this probability. Okay, specifically is given by state transition distribution probability Pj, which is you have M state to move into. Okay, but given action J and the probability is independent, so that's why we call the Markov decision process. Okay, what's the MDP problems? It turned out for stationary, this kind of a Markov decision process, if you play this process long enough, you actually finding there was a stationary policy, which means each state or each agent always play that same action. That's the optimal. Or you can think about it, each one have many cards to play, or you have a winning card or optimal card to play with. So the question is how to find that winning card for each state, which is pi 1 to pi m number of states. Okay, so always choose. Okay, MDP again to find it. So usually, because this is an infinite horizon problems, we usually associate it with a discount factor, which means the future value is discounted at the present values. So this is a pre-standard assume, and we have to assume future is discounted as today. Okay. On the other hand, this is the Markov decision process. If the states actually are partitioned into two sets, one actually is trying to minimize, another set is trying to maximize. Then the process becomes what we so-called two-person turn-based zero-sum stochastic game. So that's typically people formulate this play game and typically with this kind of things. So you have your play card and you have one to maximize, one to minimize, okay? So this is called a stochastic game. Typically discount factor gamma, which is 1 plus rho. It's basically interest rate stuff. So that's the standard, okay? So this is toy examples, okay? I have 0, 1, 2, 3 labeled as states. This is the toy. This is called an absorbing state. Okay, all these edges can be represented as this flow, as a graph. Okay, as edges. So I take for this state, they can take red actions or take blue actions. If you take red actions, for sure you're going to move into state 1. If you take blue actions, then 50% you move here, 25% over here, 1/8 move over there, and also 1/8 move over there. So that's what it's pattern. Okay. So you can, that immediate cost, action cost, can associate as edge cost for these problems. So I'm going to have a 0, 0. Every action have a 0 immediate cost. But however, there was a cost, which is at a state 4, there was no choice. You have to play this action, then you pay $1 million, whatever. So that's the, okay. The question is, what is the optimal policy for these agents, for all the agents, if they want to play this game, whatever. And you can see the optimal policy would be red, 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 blue, and reach this observing state with no cost. Is that clear? Okay. So that's the optimal policy. Okay. So you can think about this, repeat again, but this is a toy example. Actually, one-time optimal strategy would be also optimal for infinite horizon anyway, whatever. The question is, how can we find that policy? Red, 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 blue, okay? So this is a thing, okay? I just simplified this a little bit, and instead of put too many edges over there, I just say you have a 50% here, 50% here, then 50% here, 50%. So it just simplified the graph. Looks like a little bit cleaner, whatever, okay? But it's the same thing, whatever. Well, it turned out finding such an optimal policy or finding an optimal solution for that problem can be formulated as a linear programming problems. Okay? So this is all the J here are all the actions associated with the first agent. So you just need to finding Y1, which is a value for that state, which is less equal to Cj plus gamma, that's our discount, which is Pj times Y. Okay? This is true for each state, and you just maximize the sum of all the Yi. It turned out, and this is a linear programming formulation for infinite horizon and MDP problems. So if you solve that linear programming problems, you can find it. Okay? So this is problems. Okay? In some way, this is usually in the linear programming language, we call this is like a dual standard form. Okay? So this is have inequalities, and you maximize and everything. Okay. So it's the dual form. Here's the interpretation. Probably many people know Y actually represent, especially present the cost to go value of M states. That's if you learn the MDP from other language, and that's what it is. Okay. It's just actually the finding optimal cost to go values. Okay. That's the linear programming problems. So actually, choosing Y, there was another interpretation. Your maximum Y actually is try to find a fixed point such that Yi star equal to mean Cj plus lambda Pj T. I should have a Y star over here as well. So this is actually a fixed point. So you have this Y on the both sides. Okay. Then the optimal action is just the argmin of that things. But again, this should be Y star, and this is another one. Is that clear? Okay, so it's fun to find a mix. Okay. In the game, the fixed point is for some state you have a mean, for some you have a max. So that's again, it's still fixed point, whatever. Okay, so that's the difference between this. I'm going to talk about what's the recent advances on both sort of Markov decision process, uniform mean, or you actually have some people want mean and another want max. Okay. So here's the cost to go value. Okay. For example, it really depends on your policy. Suppose you take a red actions. If you take a red action, what's the cost to go value for state number 4? For sure, you have no choice. You have to pay $1 million. Okay? Then, since this guy enters this guy, so $1 million. If you have a discount, 0.9, then that's $900,000. You can do this. Okay? Here, I'm assuming no discount. So that's what the cost to go values to this. Okay? Well, is this value a fixed point? No, this is not a fixed point, because at this, 1 is not equal to mean of these 2, because you go here, it's zeros. Okay? And is that the fixed point for this state? No. If you go here, it's 1, but you go there, and you have a half percent over there, actually it's only half. So this is not the optimal policy. At the same time, it's not the fixed point. Okay. Well, here's the primal LP form of the MDP. When you have a do, you have a primal. So you can write this as a minimized sum of Sj over all the actions. Here, assume the action, all n actions partitioned into m different group. Okay, some for example, 1 to 5 for the first state, or 6 for 10 for the second state. So you can just write this. Eij is 1, when j is, well, it's easy to write. Okay. The primal variable represents expected action flow or frequency. That is the expected present value of a number of times action j is being chosen. Okay. So this is, or you can think about it, this is more like a generalized network flow level. Okay, discounting. Then when you can also actually have a different discount factor for different action. So if all the gamma has the same gamma discount, we say MDP has uniform. Otherwise, we say have a non-uniform discount factor. Non-uniform discount factor is more similar to generalized network flow. So generalized flow means when you flow in, flow out, may different, whatever. Okay. Has some kind of a discount or leakage or something. So here's a couple of algorithmic events of the MDP. Okay. Shapley and Bellman developed a method called value iteration, because this is a fixed point operations. So it just continue to operate. You know, it's like you can prove as long as you have a discount and mapping is contractions, and you can do it. Okay, but that's a continuous iterative process. Another best-known method is due to Owen Howard. Okay, 1960s. That's our colleague, and it's known as a policy iteration method, which generates an optimal infinite number iteration in somehow a very distributed and decentralized way. So you have a policy. You compute the cost to go values. Okay? Then you broadcast this like a message passing to all the states count these state values. Then they find out what's the best response. Okay? Very autonomous, very decentralized. So that's the process. So that's why people like this process, because they can be implemented in very, very distributed, decentralized way. And also, yes?
The computation of the cost to go seems to require...
Yes, yes. But however, you need to have a centralized guy take any action, then somehow centralize the convert. So people usually update it. It's like a matrix inversion, whatever, in that case. That's right, it is. That's right. And but value iteration is much, much cheaper. That's right. Yes, correct. Okay. But in terms of finding optimal policy, probably, and have some kind of a matrix or invention, and yeah, you need someone over there. But well, the simplex, on the other hand, because you can formulate as a simplex method, so simplex method can also help to solve. Okay, so somehow, and it's also very popular. So you update one at a time. So as I said, and the simplex method in 2.0 are very alive for MDP. But however, for MDP, my knowledge is most people just use policy iteration. Yeah, because so it's still fast, because in 2.0 even need to inverse an even bigger matrix. So, so this is what people usually use. Okay. So yes, you have to do the cost to go values. Okay. Again, this is the cost to go value. So what's the policy iteration method? Policy iteration is once we understand the cost to go value, then we can evaluate expected cost for each actions. Then each state move to the cheapest one, to the mean one. So in this case, and this one go here is 1, go here is 0, this one go here is 1, go this is half, this one go this is 1, go this is 3/4, this one go here, this is 7/4. So policy iteration just move. Here I'm just showing red actions are actually chosen. Okay, and you have a new, that's just like Rob said, you have to, Bob said, you have to compute the new, computer that could be very demanding, but people can use some other method, iterative method to solve it. Okay, so this is this one. Another is the simplex. What's the simplex method? Simplex method actually is switch one state at a time, whatever. So that's what it is about. Okay, and so you, for example, previous one, this one, there was an index rule. Everybody, you always switch, because in the simplex method have many ways to improve. Which variable you pick enter the basis, you always smooth the index. So in this case, you took a smooth one, then switch over there. Okay. On the other hand, the original George Dantzis rule is which state switch action will create the largest improvement. Then that's what George Dantzis rule. So for George Dantzis rule, they will switch from 1 to 0s. So once you do that, what's the new cost to go value? Then you have 1, 0, 0, 0. In this case, it turns out it is optimal. Okay. So it turns out people already find, even for this toy example, if you use the smallest index rule, if you follow this kind of rule, it turns out even for this small problem, you need 2 to the power 5 steps to converge. Okay, because whenever you switch, the next time you switch this, once you switch this back. Okay, it's just alternating. So this is a very cute example to show if you follow smallest index rule for MDP, actually your exponential number steps. Okay. This is a story. Okay. So now basically, however, for this problem, you switch like this, or you switch like a policy iteration method. I just want to show the greedy rule is good. It's not a coincidence. Actually, you can prove a bound. Okay. So this is here. I'm just talk about polynomial time algorithms, computation time algorithm, total number, and whatever, and it's a polynomial in Mn. If you also depend on the bits and the data, then it becomes polynomial. If only depend on Mn, it's become strongly polynomial time. Okay, so I know this is for, I don't know if this is a kind of complexity classification still popular in computer science or not, but still very good theoretical question, even for today. You may argue, so today Mn just getting too big, even polynomial is not good. But then I have no words to say what we do, whatever. But in practice, people always do dimension reduction or do some approximation or sampling or whatever. So reduce the dimension. So, but anyway. So given a problem Mn, can you find a strongly polynomial time algorithm to solve these underlying problems? Okay. The standard proof for polynomial time algorithm when the gap between the objective value of current policy. In this case, you can prove every policy is like a basic feasible solution for the linear programming problems. Okay, 2 to the minus L, then current policy must be optimal. But this kind of a gap argument it can be used to prove strong polynomial time, but not be adequate to prove strongly polynomial. Okay, because the argument has to be more combinatorial, whatever. Okay. Okay. There was many negative results. I already mentioned. Smooth index rule actually is not. Also, 2010, Fanny said, exponential number iteration even for undiscounted finite horizon MDP. Okay. Freeman, Hansen, Zwick, and also give an MDP example to show random pivot rule needs exponentially many steps as well. Okay. Freeman also so-called Zada rule needs exponential many steps. So all those are different rules, and it basically say, and for somehow still simplex is still overwhelmingly negative. Okay. That's what I started this very well. So many efforts has been fed. So many counterexamples are some extreme cases. But here I'm just say go back to original discounted infinite horizon MDP. Okay, so what's this? It turned out, okay, here's the theorems. Okay, the classical simplex method, Dantzis pivoting rule, and the policy iteration method starting from any policy terminate in n times n minus n 1 minus divided by 1 minus gamma log m squared 1 minus gamma iterations. That's it. There was no big constant found it. Okay. Everyone still remember what's gamma? Gamma is the discount. So you say if next year's value is 0.99 today, then gamma is 0.9. So what this tells you? This tells you actually if gamma is fixed, treat them as a constant, which normally we do even other implications. And this is actually quadratic time in terms of n. That's pretty much people more or less observed in practice. Quadratic number for simplex method steps. Okay. Okay. Well, soon after, and Hansen, Midround, Zwick, ACM 12 published it. Okay. They said policy iteration method actually terminates in n over 1 minus gamma log m1 steps. The proof is pretty much follow the original proof in terms of the overall structure, but it's very intelligent, did more detailed analysis. So what this means, that's policy iteration actually linear time if gamma is fixed, which again is what people conjectured in practice. Again, what is the m? Number of states, and total number of actions. So this is, but as Bobby said, you need more computational time to compute the cost to go values in this step. But here you only update only in quadratic time. Okay? What is the high level idea of the proof?
Quick question.
Yes.
So the Dantzis rule was the greedy rule?
Yes, that's the greedy rule. Yeah, the most negative reduce the cost. Yeah. So you basically, as I said, what's the optimal policy? Optimal policy is a winning card for each state. So there was some non-winning card. You have a non-optimal action, optimal actions. So we basically create a non-optimal, which is what is the non-optimal action? The action would not be included in the final optimal policy. We say that action will never enter the policy again. Because you constantly generate a new policy, it's a trial policy, intermediate policy. But that action is somehow eliminated. I don't know which one eliminated, but now there was one eliminated. Okay? And also it's there, okay? It's fixed. Okay? So the event will happen in most certain polynomial number iterations. More precisely after m over 1 minus gamma, look these iterations, a new non-optimal action would be eliminated from appearance any future basis or in MDP language in the future policies. Okay? The event can repeat another non-optimal state. So you only have this many of to be eliminated. So and this times this, and that's it. That's okay. What Zwick proved is actually you only need the 1/1 gamma iterations in policy iteration method. A non-performing or non-optimal action will be implicitly eliminated. So that's the high-level proof. So it's very combinatorial, very elementary as well. Okay, now what happened to 10-based two-person zero-sum game? Okay, as I said, the set is does not. This is an interesting problem from computer science point of view. Even up to date, we still don't know whether this problem for MDP, because it's a special subclass of linear programming, it can be solved in polynomial time. But for these problems, we still don't know whether it's polynomial solvable or not. If even you can't discount as variables or whatever. Okay. It does not admit convex programming, like linear programming we mentioned. Okay. Still unknown. Okay. However, in the same ASM12 papers, there was a method to solve these game problems. It's called the strategy iteration method. It's like a stack bug game. So I want to minimize. Whenever I played, I assume my adversary followed exactly to maximize the things. So it's like I'm a leader. I change my cards. My follower always respond in the best interest. Okay. It turns out you can similarly transfer this policy iteration method to this strategy iteration method. Again, this is about how much you reach the optimal strategy, which is optimal for you. Okay. So if gamma is fixed, then this becomes linear time algorithms. So this actually is the first polynomial time algorithms, and this kind of factor is fixed. Yes.
You said it's still unknown if it can be solved in polynomial time, and then this is.
But here you have to assume gamma is fixed.
Got it.
Okay. Yes. So if gamma, but this is the bound. Yeah. This is true for gamma fixed or not fixed. But you want to make this statement, this stranded polynomial, you have to assume gamma is fixed. But that's what it is. Yeah. Yes.
Before you said that there are like lower bound results for MDPs, do they apply here also when gamma is not fixed?
Yes. With gamma is not fixed.
So if gamma is not fixed, there are examples which require
yes.
time.
That's right. That's right. That's right. Like Finney, whatever. We already have examples. So discount played a big role here in terms of the computation.
Exponential description, just in terms of the complexity.
The distribution, whatever. Yeah. There was a.
It's conceivable there's a different way of describing it.
Basically, they can construct the worst examples, whatever. But overall, they're still like for linear time. You're right. Yeah. Okay. So this is okay. So follow this kind of a result, and I saw a couple of interesting results. It's called the robust MDP with discount. Since we talk about the decision making and uncertainty, a very popular model is called the robust. In many MDP applications, state transition distribution may be uncertain or long in advance. So I saw many applications, even today's. Okay. So the robust MDP would assume that when a decision maker places actions, adversary rate would always choose a worst distribution to maximize the expected goal loss. Okay, so this is the typical min max. Yeah, so this is the adversary state. It's like the MDP game, whatever. Okay, they always want to maximize. So you just create the adversary state. After each actions, he can choose some distributions among his pocket, and whenever that distribution he can take a look cost to go values, they choose the maximum distribute the value, maximize that actions to give to you, whatever. Okay? So somehow, this robust MDP is actually a special case of this stochastic game. So that's very easy to see. Of course, depending on how many distributions you can choose, and this is the total number of actions, and the number of states become n plus m, so this is number of iterations. So this is a so-called robustic MDP. So you basically, robust MDP can be represented as the time-based stochastic game. I'm doing okay in time? Okay. So this can be over there, okay? Okay, I think you guys ask a very good question. All this still depend on the gamma. So yeah, the nice thing is they don't depend on anything else. Distribution, how mass it is, how this is. But the bound still depend on gamma, okay? As David also said, MDP actually, even we assume gamma is very, very small, but somehow practically still works very well, whatever, okay? But we do have some bad examples. So the next question, what we did is, we try to tackle this called this deterministic MDP, okay? We try to see, in general, we cannot get rid of gamma, dependence on gamma, but maybe for certain subclass problems, and we can get rid of gamma, okay? So one particular problem is, we assume the probability distribution contains exactly 1, 1, and 0 everywhere else. So that's like, whenever you take action, for sure, you know which state you're going to enter, okay? Is that clear? Okay, so that's called the deterministic MDP, but this problem actually is trying to find generalized cycle flow problems, okay? Here's the theorems, okay? And we somehow succeeded, actually get rid of dependence on gamma. It's regardless of what gamma, how close to 1 it is, and how big it is. The deterministic MDP, okay, terminates very bad bound, okay, m to the power 3 n squared log square m iterations. Yes?
Is this for the greedy pivot rule or for anything?
Greedy. Only for greedy. Okay. This is assume all the actions have the same discount factors. If the discount factor is different, as I said before, that's more like even higher, whatever. But nevertheless, I do have a constant over there. It's somehow 8 times something, whatever. It's not like 1 million or something, whatever. So it do have a bigger O over there because there was some overhead cost, but it's the constant, nevertheless. So here's the, for deterministic MDP, simplex method, it is strongly polynomial. Even for any gamma, okay? Even gamma arbitrarily close to 1. Okay. So this is, so somehow, put some positive news for it, okay? And also Hansen and Civic, they can reduce 1 factor m from this bound subsequently by more careful analysis. Okay. The bound is very bad, but the proof is interesting. Okay. So maybe, as I said, and all this proof has to be very combinatorial. You cannot just like simple things. Okay, yeah, put it down. It turns out each policy can be represented as a graph. As I said, each policy is to choose 1 action from each state, right? So it could be like this, then forming a cycle, or could be every I is a cycle level, okay? So you want to find one with all different discount, you want to find such a structure where this structure have a minimum discounted cost. That's what it is, whatever, okay? So if you, okay, then there was 2 types of things, structures on this graph. Some state you have action is only on edge. Now some stage you have this on the cycles. Okay? So we basically say you have a path edge, you may have a cycle edge in any policies. Okay? And also, the expected frequency, I'm talking about the primal values, the frequency flow values. Once you have this cycle, you cycle infinite horizons. Once you have edge, you only pass this once and then enter over there. So those flow values at the edge is very, very small. But at a cycle are very, very big because they, especially when discount. So you have these two types of pivots. Whether the edge you choose in on the new policy is on the cycle or on the edges. Okay, so this is a proof. I'm talking about a uniform discount. The newly chosen action is either on a path or on a cycle. Okay, then you average this number of consecutive pivot steps. There must be at least one step that is a cycle. Once you only change the path, the only small improvement in the simplex method. Okay, but once you have a pivot, the newly chosen edge is on cycle, you make a big improvement or whatever. So the question is, we have to bound it. So in some sense, there was two layers. You know, so you first pivot, you wait until big pivots, and then you have to perform lots of small pivot, but you can bound it. Okay. And this is the M cycle pivot step. This non-optimal action would never be chosen again. So it's like one, like what I proved before, everybody's one layer. But here you have two layers. Okay, so you pretty much for non-uniform discount case, they actually have a different levels. Whatever. Okay, so each, then you just formulate. And try proof. For example, the proof is much more involved for this non-uniform cycle, but a uniform, basically this times this, gives you a total number of steps. Okay. So very elementary, very combinatorial. Okay. More result, and this result was extended to general non-degenerate LP. Cassava and Mizuno, okay? So they basically say, and all this analysis is applicable to non-degenerate linear programming algorithms, okay? Non-degenerate means every basic variable has a positive values, okay? So my 1 over 1 minus gamma is like 1 over smallest positive values in those basic variables. So that proof is very simple, okay? But however, if problem is degenerate, I still don't know whether there was a polynomial algorithm to get out of the cycle or whatever. A simplex method. Yeah. Even the yeah. So this is I still don't know. Okay.
The cube examples.
Yeah.
Non-degenerate.
Non-degenerate.
No, I mean
the simplex method. Actually, the worst case for simplex method is non-degenerate.
It's non-degenerate.
Yeah, it's just the value is just like gamma, very close to 1. Yes, actually, many of us it's not about degenerate or non-degenerate. Okay. And also create a renewed exciting research on simplex method and also linear programming. So a couple of papers very recently, and Fernie Savani, you know, and also people here, and also did some nice work and tried to prove simplex method have this complexity result. Okay. So in some sense, simplex method, the research is still very alive. Looks like still has some way to go. Okay. So I'm going to make, I only have 2 pages left. I'm going to make some remarks. The performance of simplex method is very sensitive to the pivoting rule, looks like. Yeah. So, of course, and people still looking for whether there was a good pivoting rule and can handle all the cases. So we still don't know, whatever. Okay. But at least for MDP, we saw what's the difference between smallest index rule and the greedy rule. Okay. So talk about, as I said, policy iteration very decentralized. Okay. It seems works under this kind of Markov properties. Okay. And it's just people best response to some messaging, and I know it's also very popular now machine learning, this message passing algorithms and stuff. And yeah, it's just everybody decentralized, and for your own interest, take the best action yourself. Okay. So that's what the policy. Okay. A gradient steep descent works when there was discount. Okay. So that seems natural, and because the discount future value, so gradient should be a good rule. Okay. Multi-updates pivots work better than single update. It's like in the provable case, we prove the proved iteration is better than simplex on the overall number of steps. Okay. So that seems works. Okay. Also, this kind of a method, because it's so decentralized, so you can easily combine with dynamic sampling to deal with a large number of actions in each state. Okay, so people right now solve some problems. Yeah, if you use this kind of things, with large, if number of actions too many, of course, it's still not good. So what people usually do is to sample some actions, then just prove some state. Okay. So this is okay. Yeah. I saw a couple of works and also solve online MDP. It's like an MDP for each state. The actions reviewed sequentially. Okay. So it's like LP problems. You only have a few columns, but you have many columns to add into these primal MDP forms. Okay. So the question is, if only can you dynamically update your policies until actually to get a good complexity bound, and even n is very big. Okay. This I think Shipra did some nice work on tackle general linear programming. One column is one linear programming. The matrix revealed from left to right sequentially, whatever. But at each time, you have to make a decision, whatever. Okay? So this would be a good online. Okay? And then policy iteration just update and update. I believe the cost to go value must have some concentration so you can prove some nice theorems. You don't need too many samples, whatever. Okay? On some permutation or some generation. Okay? Is simplex strongly polynomial for deterministic MDP game? We proved the simplex method. It is strongly polynomial for deterministic MDP process, which means only have one group to minimize. What about for game? If you can prove that, that would be actually, I believe that's a good big step, because again, for complexity for game is virtually unknown in many aspects, especially when gamma is also variables. Okay. Is policy iteration method strongly polynomial for the deterministic MDP? I proved Young Post, and I proved and the simplex. It is strongly polynomial for general deterministic MDP, means gamma can be arbitrarily close to 1. But however, we're not able to prove for policy iteration method. Okay? If it works, that very high complexity bound should be come down, because, as I said, for discounted MDP, when discount is fixed, and policy is a linear time and simplex quadratic time. So it's very intriguing, and we don't know what to do. Okay? So it looks like everything works for simplex should be moved to policy, but that's the case, and not able to do it. Okay. Instead, was actually for MDP game again, and we still don't know even the game can be solved in pitas, whatever. Okay. So this is, as I said, and it's very tough problems, but many real problems like robust MDP actually can be formulated. It's a strong polynomial for MDP. I will only be able to for deterministic. Okay. For non-deterministic, we have to assume gamma is fixed. So this is since whenever gamma is fixed, everything is nice, extremely nice. Not only polynomial, strongly polynomial, but however, for this kind of varies, we don't know much. So this is like very, very troubling, whatever. Okay. Of course, the big picture is still strongly polynomial time for LP. As I said before, and the people nowadays may not be interested in this as a computational problems, but however, it is very, very intriguing. And I think still, since this is a theory of computation, Science Institute, so I hope some people here can answer that question. Thank you very much. That's all.
We have time for a few questions.
Yes. Okay.
What's known about lower bounds on the number of iterations for policy iteration? For example, do we know any examples of MDPs that require more than 3n iterations of policy iteration? For any discount factor?
Yeah, for any discount factor, people actually have they can construct example actually have a sub-exponential lower bound. So
It's like 2 to the n to the epsilon.
yeah, 2 to the some n over epsilon or something, yeah, or over epsilon to some power or something. Yes, it's sub-exponential. It actually n is in the exponent.
Okay.
So in general, as I said, if discount is not fixed, we do have examples to show policy and simplex both need sub-exponential. I believe that people later on also construct an example, not only sub-exponential, but also exponential. So for discount, the simplex cannot be work, and policy cannot work. You have to have some new algorithms. Maybe combined with some interior algorithms, whatever. Maybe you can create some combinatorial interior algorithms to do this. That's what Alex Madre did something for maximum flow. Looks like a very intelligent combine some combinatorial things for uniform maximum flow, right?
Let's thank this man.
Okay, thank you. Yeah.